Hello everyone, let's take a look at our next problem. This problem was submitted to me by a viewer. Some numbers could be represented as a sum of two squares, some are not. For example, 5 is equal to 4 plus 1, 13 is equal to 9 plus 4, and 4 is equal to 4 plus 0. But 3, 6, and 7, and others, cannot be represented as the sum of two squares. What is the ratio of the numbers from 1 to n that can be represented as a sum of two squares as n tends to infinity? Okay, so this sounds like some kind of number theory problem. Of course, the set of numbers that can be written as a sum of two squares is countable, but we're looking for what proportion of numbers less than n can be written as a sum of two squares, and then we want to take n to infinity. So one of my thoughts is maybe if we can figure out some properties, like if a number can be written as a sum of two squares, maybe there are some other properties that it has that would make the proportion of numbers that can be written like this a little bit more obvious. Like one thing I'm thinking perhaps is if we consider whether A and B are even or odd and all the possible combinations of that, and then see if there's like maybe we can conclude some property about A, the remainder when A is divided, or when n is divided by some number, and if it's restricted to be some quantity, then that would give us a hint as to what the maximum proportion could be. I'm going to fool around with that idea for a minute and then see if I have any other thoughts. Okay, so if n is written as the sum of two squares, I have all possible combinations here. It's either a multiple of 4, or it's 2 greater than a multiple of 4, because we have 2 1s in here, or it's, oops, this is a typo, that shouldn't be a 3, that should be a 1, or n is equal to 1 mod 4. So it's impossible to be a sum of two squares and also be equal to 3 mod 4. So the proportion of numbers that can be written as a sum of two squares in the limit, at least, is bounded by 3 over 4. So if Pn is the proportion of numbers less than or equal to n that can be written as a sum of squares, then this should be true. My instinct would tell me that it's probably a lot less than that, though, because as you get really, really large, the squares start to spread out. On the other hand, you do have an extra degree of freedom in some sense. So according to in the examples that were given, 0 was used, so we're allowed to use 0 as one of our squares. So of course, all perfect squares themselves will go in the top row here. I wonder if thinking about this sort of geometrically makes sense. Or maybe, hold on, what if I write it as What if I rewrite this as a squared is equal to n minus b squared? Then n minus b squared is itself a perfect square. Even though n may not be a perfect square, I could write this, but that's not going to help us, because if n is not a perfect square, then neither of these two things will be integers. So if I draw on the plane the equation represented by a squared plus b squared equals n, I of course get a circle of radius root n. And what we're looking for is whether this circle passes through any grid points. If it does, then n can be written as the sum of two squares, but this is not, I don't know if there's an easy way of doing this. Wait a minute. No. I'm not sure. This kind of thing is completely out of my area of expertise. I mean, we have an upper bound, but I have no idea how close that would be to the real, to the true answer. Maybe the way to think about this instead is find, look at every single grid point. Look at every single one of these grid points and take one of them, for example, here. There will be a circle that passes through that. So draw the circle that passes through the grid point we're considering, and then we need to make sure that this number here, when squared, gives an integer. And I suppose this number, so that's the radius of the circle. So we have A, we have B. I'll call the radius for now R. We have R squared is equal to A squared plus B squared. I don't know. I might just have to think about this one in the back of my head for a while. It's possible that this is significantly more difficult than anything I'll be able to solve, but I'm going to take a break from this one for now. At least I came up with this bound, so I'm half satisfied. Thanks for watching.